Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So in this video, we will be learning about articulation point. What do you mean by articulation point? Now, if this is the given graph, any node on this graph on whose removal the graph breaks into multiple components is what you call as articulation point. Like if you see this graph, for an example, imagine I remove 0. Do you see the graph being broken into 1 and 2 component? Do you see that? You see that, right? The graph got broken into 2 components on the removal of 0. Similarly, if I try to remove 2, like if I try to remove 2, did the graph break down into multiple components? Yes, it did. One is here and the other one is here. The graph broke down into multiple components. Yeah, these edges will no more be there, but the graph did break into multiple components. So, any node on whose removal the graph breaks down into multiple component is known as an articulation point. Now, can I say that 3 is an articulation point? No, I cannot, because even if I remove 3, the graph is still connected. I don't see any breakage apart from the removal of 3. That is why 3 is not an articulation point. For this particular graph, only 0 and 2 are articulation points. Now, in order to understand articulation point, there is a prerequisite, and the prerequisite is this particular video, bridges in a graph. The video before this in this particular playlist is what you should have seen. You should have understood what is time of insertion, what is the lowest time and everything. And if you know that, then only you should watch this particular video which is talking about articulation point. Because I'm assuming you've seen the video of bridges in a graph, because the concept that we have used in bridges in a graph is what we will be using in the articulation point. So please go back and watch it and come back and watch this video again. So if you remember the bridges video, we used 2 arrays. One is the time of insertion, while the other one was the lowest time of insertion. Now, the definition still stays the same, but there's a slight tweak. Over here, the time of insertion states while you enter in the DFS, you store it. But the lowest time of insertion has been changed, and it states minimum of all adjacent nodes, like you take all the adjacent nodes apart from the parent and take all their lowest time of insertions, but you also remove visited nodes. Do not take parent and do not take visited nodes. Why not visited nodes? I'll explain you. In the bridges video, there was nothing as visited nodes. There was simply apart from parent. Over here, it's apart from the parent and apart from the visited nodes. Why? We will be talking that in depth when I take this example. So if you did not understand the exact use of flow, do not worry. When I do a dry run on this particular graph, you'll get an idea about what is the exact definition of flow here, because it's slightly different from the bridges in the graph. Okay, so in the bridges in a graph, if you remember in that video, the condition was very simple. If the low of IT, like if the low of IT in any case was greater than the time of insertion of the node, then we could say that node and IT is a bridge, right? That means if the adjacent node cannot reach back to the node or before it, that means it is a bridge. This was the condition being used in the bridges in a graph of video. Now over here, we removing an edge? No, we're removing the entire node. We're removing the entire node. So if you're saying this is an articulation point, the 5 has to reach before, not at this node, not at this node. In the previous bridges, if you could reach at 2, it was okay because the edge was removed. Over here, you have to reach before 2, somewhere before 2. That is why we'll slightly change the definition of, we will say, hey, if the low of IT cannot reach, that means if it is greater than the time of insertion of node, that means it can either reach the node or it is greater. Even if it's reaching the node, that is of no use because I'm going to remove the node. So even if you reach node, that's of no use. So this is the updated condition. This is the updated condition. And there's a slight new introduction, and that states parent is not equal to -1. Yes, we have a slight new introduction. We say parent is not equal to -1. Why parent not equal to -1? Let me explain. So imagine if you have a graph like 0 and it points to 1 and then it goes to 2 and then goes to 3, right? So apparently if you're at 0, if you're at 0, 0 can never be the articulation point. Why? Because even if you remove 0, it still stays as a component. It still stays as a single component. So be very careful. If it is the starting point, do not use the formula. You will go wrong. You'll go wrong. For the starting point, we will use some different logic, which I'll talk at the back end. But as of now, remember, if it is the starting point, do not use this formula because this is of no use. If you remove, it's of no use. The formula is of no use. So do not use this for starting points. For starting points, we'll use a different logic. Okay. So I hope you've understood. You have to reach before the node, not at the node. You have to reach before the node. Okay. Now let's quickly start our time of insertion. So let's start the DFS traversal with 0. Market is visited. So what are we storing? Time of insertion and low, similar to bridges. We inserted at time 1 and the lowest time is 1. Next, we go here. So market is visited and 2 by 2. So does 1 have any of its adjacent? No. So we will go back. When we go back, will we apply the formula to this particular guy? Because we have came back from a node. The DFS is completed. But if you remember, it stated that's the first guy. Parent is -1. Do not do anything for first parents. Do not do anything for first parents. Okay. Go to 2. So we'll go to 2 and we will update it like 3 by 3. Similarly, it will go here. And the moment it goes here, it will update it by 4 by 4. But here comes the twist. So it says, I have updated myself by 4 by 4. I've updated myself by 4 by 4. But I can go, but it's already visited. I can go, but it's already visited. So what I will say is, hey, listen, I will just update my low. I'll just update my low. But while updating my low, I will just take this and not this. Why? I'll explain you as we go forward. We will not look at this. We will just look at the time of insertion. And that is what I'll take. I'll update it with 1. Perfect. Time to come back. Now when it comes back, the low looks around it and says, you have 1, you're not my parent, you're not a visited node because you did your DFS. Since you did your DFS, give your low to me. That updates its low to 1. Now, can I say the DFS of 2, call the DFS of 3 and now it's back. Now since it is back, 2 will say, okay, wait, I have done a DFS. Now let me see if I can be an articulation point. Now, what is 2? 2 is stating my time is 3. 2 is stating my time is 3. So 3 is saying my lowest is 1. So I can reach before you. So even if you're an articulation point, I can still reach. So even if you're removed, I'm still somewhere in the same component. So this will not be an articulation point as of now. Right? So this is why I said greater than equal to. This is having a lowest point of 1. This is having an entry point of 3 and it can reach before 3. So this is why this is perfect. Perfect. Let's go down. So 3 is done. Now we'll go to 4. It'll be like, sorry, my bad. It'll be like 5 by 5. We have 5 by 5. So it says I have 5 by 5. Right? So it marks it as visited. Next goes to 6 by 6. Marks it as visited. Next goes to 7 by 7. Marks it as visited. Now here comes the critical junction. You have 5. 5's DFS is done. Why? Because 5 has one adjacent node which is already visited. So now the low says, I will look at the adjacent node, but that's visited. So I will not take 1. I'll not take 1 if it's visited. I'll not take 1 if it's visited. Instead, I'll just take 3. Why? Why is the question? I'll take 3. Why not 1? Why not 1? Because in bridges we took 1. We took 1 because I was greedy. You need to understand. Now this node was visited. Why was it visited? Because I traversed like this, then I went here. Now I did not take 1. Why? Because just imagine, I remove this 2. Can you reach back to 1? Had you taken 1, just tell me how will you reach 1? You cannot. So if it is a visited node, do not take something which is via 2, because 2 will be removed, might be removed. That's why you'll always take 3 and not 1. Got it? So can I say the DFS of 5 is completed? And now it will try to come back. So when it tries to come back, see what happens. So I can say DFS of 5 is completed. So the call came in from 6. Now it goes back. Now 6 is saying, okay, what is the entry point of 6? That is 6. What is the entry point of, like, where can 5 reach? 5 can still reach 3. That means it can somewhere reach 6 back again, right? Even if you remove 6, it can still. It's a part of the same component. This cannot be an articulation point. Go back. So when it now goes back, 4 says, okay, you're coming back. Let me take yours because you are an adjacent node. You're not a visited. You are one of my adjacent node who went into DFS, completed it. I'll take your 3. I'll take your 3. I will take your 3. Now, this time what happens is 4 called 6. Now, what is 4's entry point? 5. 6 says, I can still somewhere go and reach 3. So I can still reach before you. So you cannot be an articulation point. Perfect. Now comes the critical junction. 4 now goes back to 2, stating I'm complete. I'm complete. So 4 is complete. It came from 2. So now it goes back. 2 says, okay, you're done. What's your minimum? 3. My minimum is 1. No need to take it. So 2 says, can I be an articulation point? What's my entry point? That's 3. What's your minimum entry? You can just reach 3. That means you can reach to me, not before me. Not before me. So even if I remove myself, you guys will be two separate entities. So thereby, 2 is an articulation point. Thereby, I find 2 is an articulation point. So I can say 2 is an articulation point. Got it? Very simple, very straightforward. The only reason we did not take 1 is because had we taken 1 over here, this one would have been propagated here, this one would have propagated here. And I somehow would have said I can reach 0, which is not possible because it's via 2. It's via the visited path. That's why you do not take visited, because if a path is via visited, that's no point. I want to go via some adjacent nodes. Got it? Perfect. Now 2 says, let's go back. Now when I go back, again, the parent is for this -1, so I'll not consider. So mostly done. The updated condition says I should reach before this. And the parent should be -1. And low should only update itself if it's not parent and not visited. If it's visited, it takes the time of insertion. Simple. Done and dusted. Now the question comes, is 0 an articulation point? It is, because if you remove 0, split it into 2 components. So the logic over here is very straightforward. And now imagine there is a node and it is like just connected to 1. In that case, this can never be an articulation point, because even if you take it off, it's still a single comp. It is not broken into multiple. So it cannot be an articulation point. But the same parent, if it is connected to multiple children's, the moment you break it, there will always be individual components. This is what happened in this case. The moment you took it, this was individual, and this was individual which was later connected here, right? So what's the grasp? If it's a starting point, and if it has multiple children's, then only I will say that it's an articulation point. So for the starting point, if it has multiple children's, then only I'll say it is an articulation point. I will not apply the formula to the starting point. Never ever I'll do that. Got it? So before moving on to the code, did you observe something? Now, when you came back from 4 to 2, 2 said I am a articulation point because 4 cannot reach back to any position before. I was saying that 2 is an articulation. Now, what if there was another component which was similar to this, 7 and then 8 and then 9 and then similar? So if there was another component, you would have again gone the same way and you've again came back and again you would have found 2 is an articulation. So it might happen during the traversal course, you might find 2 to be the articulation point multiple times. Because if I just extend this graph, just imagine I extend this graph to something like this. Imagine I'm taking it to 7 and then 8 and then 9. So similar graph, just extended into two portions. So this, when it came back, it found out 2 as an articulation. Similarly, when this goes and comes back, it will find that this is again an articulation point. So it might happen, you might find 2 multiple times. So instead of printing directly on the check of this condition, create a hashing. Say 2 is an articulation point. Say 2 is an articulation point. Say 1 is an articulation point. Just mark it. And at the end of the day, you can return it. So I'll show you this during the code implementation. So if you can see that the question states you'll be given a zero-based indexing graph. You have to find all the articulation points. And if there are none, you have to return a list which is containing a -1. What are we given? We are given the V, we are given the adjacency list. So what did we require in order to write the VFS? Sorry, DFS. We required a visited. So mark it, have this one, just keep it as N. And then you can have a T in of N. Then you can have a low time as N. That's something which you can have always. And then you can have a mark which marks which are articulation points. And then there can be multiple components. So maybe you can just scroll through and you can say if not visited of I, you can say DFS of I and the parent can be -1 initially. You can pass in the visited T in the low, the mark and the adjacent. And at the end of the day, you can say vector of int answer, and you can just go across all the nodes and you can say if it is marked as articulation point, can you please store it over here? And if answer dot size, like if there are no articulation point, they state you to return -1. So please return -1, else you can return the answer. Quite simple. Now you just need to write the DFS. So let's go across and say private, and you can have a timer as 0, and you can have the void DFS. The void DFS is int node, and it says int parent, and then you can take all the things like vector visited. You can take it by reference. You can take the T in, you can take the low. At the same time, you can take the vector of int and take by reference the mark, and at the same time you can take the adjacency list. Done. What's the first thing that you will do? You'll always, when you start off, you'll say visited marked as this, and the time of insertion, the lowest time will be marked as timer, and you can always increase the timer ++ for the next step. Now let's go across to the adjacent nodes, which is like this and this. One thing you know for sure is if it is the parent, you do not update the lower time insertion. So you can just go over here. The other thing will be if it is not visited, this adjacent node is not visited. In that case, what you will do is you will go across, call it with this DFS, and you'll pass on the visited, the time in, the low, the mark and the adjacent. And when you come back, you'll be very greedy to say, hey, whatever you brought in, can you please give it to me? Okay, done. Next is the condition to check because you're coming back. So if you cannot reach somewhere before me and you're not the first guy, if you remember, sorry, not equal to -1. If you're not the first guy, you're an articulation point, my friend. So I'll just mark it. And if it is visited, in that case, I'll say low of node, because that's the current guy, will be minimum of low of node. This time for the adjacent, I will not take the low because it's visited. I'll not take the low. Instead of that, I'll take the time of insertion of that particular visited guy. Once I've done this, I think we're pretty much done. Now I'll quickly compile this and see if it is running fine. So you see, this is just giving 2. Why did it give 2? Because for the starting point, we have not written the logic. If you remember the logic, it is very simple. Count the childs, like the unvisited child. So you can just count it. And at the end, you can write, hey, listen, if the child is greater than 1, if there are more than one child, this is definitely an articulation point. And if you are the starting guy, if you're the starting guy and the child is greater than 1, I can easily say that you are definitely a articulation point. So if you add this condition up, I think it should give 0. It does. Now let's quickly submit and see if it is running absolutely fine. Yeah, it is. So guys, I hope you've understood this, right? Shuttle change to bridges. One is you need to make sure you reach before it, not on it. Before it is very important. You don't compute for parents because it might happen. It's a single parent, and even on its removal, it doesn't matter. So it's very important for a single parent. You write it like this because it might have multiple components. So in that case, it's definitely an articulation point. If it has multiple component, it's definitely an articulation point, even if the condition is not satisfied. So for parents, you have to write shuttle different conditions, and if it's a visited guy, you don't take something on the top of it. Why? Because you came via that path. Came via that path. So if that's removed, you cannot go back. You cannot go back. That's why you just take the time of insertion and not the lowest if it's a visited one. Very, very important, this one and this line and this line. That's a shuttle change from bridges. Now, if I discuss about the time complexity and the space complexity is quite simple. 3n. And what about the time complexity? The time complexity can be said as doing a DFS traversal. So v plus 2e and then a big of n here. So quite simple to get this. So I hope you've understood everything. Now, before wrapping up this video, I have a very quick request to make. I was going through our channel statistics. Nearly 50% of the users who watch my video do not subscribe to the channel. So please do consider subscribing to the channel if you haven't subscribed yet. And if you understood the intuition, the algorithm, and the code, what are you waiting for? Hit that like button. And if you haven't checked out our DP series and the SD sheet and the other playlists, all the links will be in the description. Make sure you check them out. With this, I'll be wrapping up this video. Let's meet in some other video. Till then, bye-bye. Take care.
Whenever your heart is broken.